Welcome! In this session, we'll dive into problem number 1582, titled Special Positions in a Binary Matrix. We'll discuss the problem requirements, explore multiple approaches to solve it, and analyze their efficiency. Let's get started. In this problem, we are working with a binary matrix, which is a two-dimensional grid where every element is either a 0 or a 1. The task is to identify special positions in this matrix. A position, represented as ij, is called special if two conditions are met. First, the value at that position, mat, ij, must be 1. Second, there must not be any other ones in the same row or column as that position. Based on these criteria, the goal is to calculate the total number of special positions in the matrix. The input to the problem is the binary matrix, represented as a 2D list, and the output is a single integer, which is the count of these special positions. Let's now look at some examples to better understand the problem. Here is the first example. The input matrix is a 3x3 grid where the values are either 0 or 1. The output for this input is 1, meaning there is only one special position in the matrix. Let's break this down. The special position is at 1, 2. At this position, the value is 1, and there are no other ones in row 1 or column 2, so it satisfies the conditions. However, the ones at 0, 0, and 2, 0, are not special. This is because both of them share the same column, column 0, which violates the condition that no other ones should exist in the same row or column. Therefore, the total count of special positions in this matrix is 1. In the second example, the input matrix has a diagonal pattern of ones from the top left to the bottom right. This time, the output is 3, indicating that there are 3 special positions. The first special position is at 0, 0. Here, the value is 1, and there are no other ones in row 0 or column 0. Similarly, the second special position is at 1, 1, where the value is 1, and there are no other ones in row 1 or column 1. Finally, the third special position is at 2, 2, which also satisfies both conditions. Since each of these positions has a 1 with no other ones in their respective rows or columns, the total count of special positions is 3. Now let's look at the third example, which provides a matrix that contains no special positions. The input is a 4x4 matrix, and the output is 0, meaning there are no positions that satisfy the criteria. To understand why, let's consider the one at 0, 3. Although the value is 1, it is not special because there is another one in column 3 at 3, 3. Similarly, the one at 1, 0 is not special because there is another one in row 1 at 2, 1. This pattern repeats for all ones in the matrix, where every row or column containing a 1 also has at least one other one. As a result, there are no special positions in this matrix. Let's go over the constraints and edge cases to consider for this problem. First, the dimensions of the matrix are defined as mxn, where m is the number of rows and n is the number of columns. Both m and n can range from 1 to 100. Each element in the matrix is either a 0 or a 1. For edge cases, if the matrix has only one row or one column, any one in that row or column will be special as long as there are no other ones. On the other hand, if all rows or columns contain more than one 1, the output will be 0. Similarly, if the matrix contains only zeros, the output will also be 0, since there are number ones to evaluate. Another edge case involves sparse matrices, where the matrix is very large but contains very few ones. In such cases, it's important for the algorithm to efficiently check the rows and columns that contain ones, without wasting time on rows or columns that are entirely zeros. By considering these constraints and edge cases, we can ensure that our solution works correctly for all possible inputs, from small matrices to large and sparse ones. This concludes the problem statement, laying the foundation for solving the problem effectively. To begin, let's explore two potential approaches for solving this problem. The first is the brute force approach, which is the most direct method. Here, we iterate through each cell in the matrix to check if it meets the conditions for being a special position. For a cell at position ij, where the value is 1, we need to verify two things: first, that all other cells in row I are 0, and second, that all other cells in column j are also 0. This requires separate traversals of the row and column for every one we encounter. While straightforward, this approach has a high time complexity of O, m asterisk n asterisk, m plus n, where m is the number of rows and n is the number of columns, making it inefficient for larger matrices. Now, to optimize this, we can use a more efficient approach based on pre-computation. By pre-computing the counts of 1s in each row and column, we can significantly reduce redundant checks. Specifically, we create two auxiliary arrays, rowsum to store the number of 1s in each row, and colsum to store the number of 1s in each column. Once these arrays are built, we can determine if a cell is a special position with a simple check to see if rowsum I equals 1 and colsum j equals 1. This eliminates the need for repeated row and column scans, offering a much more efficient solution. By leveraging the pre-computed data, we avoid redundant checks entirely. The time complexity for this optimized approach is reduced to O, m asterisk n, as we only need one traversal to calculate the row and column sums, followed by another traversal to identify the special positions. This makes the solution scalable for larger matrices. Another possible method to consider is a single-pass approach, which involves calculating the row and column counts while simultaneously identifying special positions in one traversal. While this method is highly efficient in both time and space, it comes with added complexity, as it requires careful data management and is less intuitive to implement. Ultimately, we decided to go with the optimized approach using pre-computation. This strategy strikes an excellent balance between performance and simplicity. The pre-computation step is easy to understand and debug, and the auxiliary space usage of O, m plus n, is manageable for most input sizes. Moreover, the time complexity of O, m asterisk n, ensures that our solution will perform well even for larger matrices. The brute force method, while conceptually simple, becomes impractical for large matrices due to its high time complexity of O, m asterisk n asterisk, m plus n. On the other hand, the single-pass alternative is efficient but harder to implement, making it less suitable for scenarios where code readability and maintainability are priorities. A key insight that simplifies this problem is the observation that a position, I, j, is special if and only if it is the sole one in both its row and column. This realization allows us to use the rowsum and colsum arrays for quick validation, saving time by eliminating redundant checks. By pre-computing these sums, we significantly improve performance compared to the brute force approach. In comparing the strategies, the brute force solution is straightforward but inefficient, the single-pass option is efficient but complex, and the pre-computation method offers an ideal balance of efficiency, clarity, and maintainability. This makes it the most practical choice for solving the problem effectively. To solve the problem of identifying special positions in a binary matrix, we first need to understand the criteria that define a special position. A position, I, j, is special if the value at that position is 1, and all other values in the same row and column are 0. One approach to solve this is the brute force method, which systematically checks every cell in the matrix. The algorithm begins with input validation, ensuring the matrix is not empty. If the input matrix is empty, we immediately return 0 because there are no positions to evaluate. Next, we establish the dimensions of the matrix, rows and cols, and initialize a counter, special underscore count, which will keep track of how many special positions we find. These preparatory steps set the stage for iterating through the matrix and checking the conditions for special positions. The brute force algorithm proceeds by iterating through each cell, I, j, in the matrix. For every cell, we first check if the value at mat, I, j, is 1. If it is not, we skip to the next cell, as it cannot be a special position. If mat, I, j, equals 1, we then verify the row validity. We iterate through all columns in row I and ensure that all other cells in the row, except mat, I, j, are 0. Similarly, we check the column validity by iterating through all rows in column j and ensuring all other cells in the column are 0. If both of these checks pass, it confirms that I, j, is a special position, and we increment the special underscore count variable. After completing this process for every cell in the matrix, the algorithm concludes by returning the value of special underscore count, which represents the total number of special positions found. While this approach is straightforward, its time complexity is quite high, making it inefficient for larger matrices. To improve the efficiency of our solution, we can use an optimized approach that leverages pre-computed information about the matrix. Specifically, we calculate the sum of each row and each column ahead of time. This involves creating two arrays, row_sum, where each element stores the sum of all elements in a particular row, and col_sum, where each element stores the sum of all elements in a particular column. This pre-processing step takes O and *m time, where n is the number of rows and m is the number of columns. Once the row and column sums are calculated, we iterate through each cell, I, j, in the matrix. For every cell, if mat, I, j, equals 1, we simply check if row_sum, I, equals 1 and col_sum, j, equals 1. If both conditions are true, the position I, j, is counted as a special position. Finally, we return the total count of special positions after examining all the cells. This optimization drastically reduces the need for redundant row and column checks, improving the algorithm's efficiency. The key insight behind the optimized approach lies in the use of pre-computed sums. By calculating row_sum and col_sum beforehand, we eliminate the need to repeatedly iterate through rows and columns for every cell in the matrix. This reduces redundant computations and significantly improves the overall runtime. The criteria for identifying a special position remain the same. A cell, I, j, is special if it is the only one in both its row and column. This means that if row_sum, I, equals 1 and col_sum, j, equals 1, then I, j, must be a special position. Additionally, we must handle edge cases appropriately. For example, if the input matrix is empty or contains only zeros, the algorithm should return 0. Similarly, matrices with multiple 1s in a row or column must ensure that these positions are not mistakenly marked as special. These considerations ensure the robustness of our solution. To implement the algorithm effectively, we use specific data structures to manage the input and intermediate computations. The matrix itself is represented as a 2D array of size nxm. For the optimized approach, two additional 1D arrays, row_sum and col_sum, store the pre-computed sums of rows and columns, respectively. These arrays allow us to check the conditions for special positions in constant time for each cell. When analyzing the complexity, the brute force approach has a time complexity of O and *m*, n plus m, due to the repeated row and column checks for every cell, and it uses O(1) extra space. In contrast, the optimized approach has a time complexity of O and *m, because it combines the pre-processing step and a single pass through the matrix. Its space complexity is O, n plus m, due to the additional storage required for row_sum and col_sum. Thus, the optimized approach provides a significant improvement in both time and space efficiency, making it well-suited for larger matrices. The given solution calculates the number of special positions in a binary matrix. Let's break it down step by step. 1. Counting rows and columns *. The rows list stores the sum of each row in the matrix. For example, if mat, I, j, contains ones and zeros, rows, I, gives the total number of ones in row I. Similarly, the cols list is built using zip, *mat, which transposes the matrix. It stores the sum of each column, where cols, j, gives the total number of ones in column j. 2. Iterating through the matrix *. The nested loops traverse every cell, I, j, of the matrix. For each position, the algorithm checks three conditions. The value at mat, I, j, is 1. The sum of the row, retrieved from rows, I, is exactly 1. The sum of the column, retrieved from cols, j, is exactly 1. If all conditions are met, the position is special, and special underscore count is increment. 3. Returning the result *. After iterating over all positions, the total count of special positions is returned. This algorithm is efficient, as it computes the row and column sums in O, m plus n, and checks each position in O, m *n, resulting in a time complexity of O, m *n. It handles edge cases, such as empty matrices or matrices without any ones, gracefully by design. Here, we start by defining the number special method, which takes a 2D binary matrix mat as input. First, we determine the number of rows and columns in the matrix using mat.length and mat0.length. Next, we initialize an array row counts to keep track of the number of ones in each row. We iterate through each cell of the matrix row by row, adding the value of each cell to the corresponding rows count. Similarly, we initialize another array call counts to count the number of ones in each column. This time, we iterate column by column and add the value of each cell to the corresponding columns count. These two arrays, row counts and call counts, store the total number of ones in each row and column, respectively. Finally, we initialize a variable special count to 0, which will keep track of the number of special positions in the matrix. A special position is a cell with the value 1, where the row and column both contain exactly 1 1. To identify these special positions, we iterate through every cell in the matrix again. For each cell, we check if it contains the value 1. If it does, we then verify if the corresponding row and column counts and row counts and call counts are both equal to 1. If all these conditions are satisfied, it means the cell is a special position, so we increment the special count by 1. Once all cells have been processed, the method returns the value of special count, which represents the total number of special positions in the binary matrix. This implementation efficiently accounts for all rows and columns, ensuring that we only count positions that meet the criteria for being special. To solve the problem, we start by analyzing a basic example. The input matrix is a 3x3 binary matrix where each row and column contains exactly 1 1. The first step is to calculate the sum of each row and column. For the rows, we sum the elements of each row individually. For instance, in row 1, the sum is 1 plus 0, which equals 1. Similarly, row 2 and row 3 also sum to 1. This gives us the row sums as 1 1 1. Next, we calculate the column sums by summing the elements in each column. For column 1, the sum is 1 plus 0, which equals 1. Columns 2 and 3 yield the same result. Therefore, the column sums are also 1 1 1. These sums will help us quickly determine if a position is special by checking whether its row and column both have exactly 1 1. Now that we have the row and column sums, we move to the next step, iterating through the matrix to identify special positions. We initialize a counter called special_count to 0. For each cell in the matrix, we check 3 conditions: whether the cell contains a 1, whether the sum of its row is 1, and whether the sum of its column is 1. Let's go through the cells one by one. At position 0 0, the cell contains a 1, its row sum is 1, and its column sum is 1. This makes it a special position, so we increment the counter. At positions 0 1 and 0 2, the cells contain 0, so they are not special. Similarly, we evaluate the other rows. At position 1 1, all conditions are met, so it is a special position. Finally, at position 2 2, the conditions are again satisfied, making it special as well. In total, we find 3 special positions, resulting in a final special_count of 3. The output for the first example is 3, as there are 3 special positions in the matrix. Let's now consider a second example where there are no special positions. The input matrix here is a 2x2 binary matrix. The first step remains the same: we calculate the row and column sums. For row 1, the sum is 1 plus 1, which equals 2. For row 2, the sum is 1 plus 0, which equals 1. Thus, the row sums are 2 1. For the columns, column 1 sums to 1 plus 1, which equals 2, and column 2 sums to 1 plus 0, which equals 1. This gives us column sums of 2 1. With the row and column sums calculated, we now check each cell in the matrix to determine if it is a special position. As before, we initialize special_count to 0. At position 0 0, the cell contains a 1, but the row sum is 2 and the column sum is 2, so this position is not special. At position 0 1, the row sum is still 2, disqualifying it. Moving to row 2, position 1 0 has a row sum of 1, but its column sum is 2, so it is not special either. Position 1 1 contains a 0, so it cannot be special. After evaluating all cells, we find no special positions, leaving special_count at 0. The output for this example is 0. Finally, let's examine a mixed case. The input matrix is a 3x3 binary matrix where the ones are scattered differently. First, we calculate the row and column sums. Each row contains exactly 1 1, so the row sums are 1 1 1. Similarly, each column also contains exactly 1 1, so the column sums are 1 1 1. Now, we check each cell. At position 0, 2, the conditions for being a special position are met, so we increment the counter. At position 1, 0, the cell is also special, and we increment again. Finally, at position 2, 1, we find another special position, bringing the total to 3. The output for this example is 3, as there are 3 special positions in the matrix. To analyze the time complexity of the solution, consider the operations performed in the code. First, the row sums are calculated by iterating through each row and summing its elements. Since there are m rows and each row contains n elements, this step requires m*n time. Next, the column sums are computed by transposing the matrix and summing each column. Transposing involves rearranging the rows as columns, which is an m*n operation. Summing the elements in each transposed column, given that there are n columns and each contains m elements, also requires m*n time. Finally, the nested loop iterates through each element in the matrix. For each element, it checks 3 conditions: whether the element is 1, whether the corresponding row sum is 1, and whether the corresponding column sum is 1. These checks are constant time operations, and since there are m*n elements, this step also takes m*n time. When combining all of these steps, we see that each major operation, calculating row sums, column sums, and iterating through the matrix, takes m*n time. Since these operations are performed sequentially, the overall time complexity of the algorithm remains m*n. Now, let's consider the space complexity. The algorithm uses 2 additional arrays, one for storing the row sums and another for the column sums. The row sums array has a size proportional to the number of rows, which is m. Similarly, the column sums array has a size proportional to the number of columns, which is n. The input matrix itself is not modified during the computation, so it does not contribute to additional space usage. Therefore, the total auxiliary space required by the algorithm is m+n, making the space complexity m+n. Now, let's compare this optimized approach to a brute force method. In a naive solution, for each cell in the matrix, you would verify whether there is exactly 1 in its row and column. This involves iterating through the entire row and column for every cell. Given that there are m*n cells, this approach would require m+n time, which becomes highly inefficient as the matrix size grows. The current solution, however, avoids this inefficiency by pre-computing the row and column sums. By reducing the redundant work, the time complexity is improved to m*n. The space complexity also remains efficient at m+n, as it only depends on the storage required for the row and column sums. Additionally, the time complexity remains consistent in the best, average, and worst cases, as the algorithm always processes all rows, columns, and elements in the matrix, making it independent of the specific values in the matrix. To mathematically verify the big O complexity, consider the 3 main tasks the algorithm performs: computing the row sums, computing the column sums, and iterating through all elements in the matrix. Each of these tasks is directly proportional to the total number of elements in the matrix, which is m*n. Since these tasks are performed sequentially and not nested, their combined complexity is simply the sum of their individual complexities. Therefore, the overall time complexity of the algorithm is m*n. This clear linear relationship with the matrix size confirms that the algorithm is efficient and scales well with larger inputs. When working on this problem, there are several common mistakes to watch out for. First, not accounting for edge cases is a frequent issue. For instance, if the input matrix is empty or contains only a single row or column, failing to handle these scenarios properly can lead to runtime errors or incorrect outputs. Always validate your logic against these special cases to ensure robustness. Next, using inefficient nested loops can create performance bottlenecks, especially for large matrices. A brute force approach with n² complexity or worse can quickly become infeasible for inputs like a 10,000 by 10,000 matrix. It's crucial to optimize your solution by reducing redundant operations. Another mistake involves misunderstanding the definition of its special position. Make sure you clearly understand the problem's requirements, particularly if a position must satisfy both row and column conditions. Missing even one of these can lead to incorrect results. Finally, modifying the matrix during traversal can cause unintended side effects, especially if the original values are needed later. Instead of altering the input, consider using auxiliary data structures, such as arrays or sets, to track information and avoid these issues altogether. Another common mistake to be aware of is overlooking numerical constraints that can lead to overflow. For example, if the problem involves sums, products, or comparisons, be mindful of edge cases, especially in languages like Java or C++ where data type limits are more restrictive. On the topic of interviews, optimization is a critical skill to showcase. While it's acceptable to start with a brute force solution, interviewers typically expect you to refine it into something more efficient. A good strategy is to think about how to minimize redundant checks, such as pre-computing row or column information to streamline validation. Additionally, leveraging appropriate data structures, like hash maps, sets, or prefix sums, can significantly improve your solution's efficiency. Clear communication is also essential. When transitioning from one approach to another, articulate your thought process to demonstrate a structured and logical problem-solving approach. Finally, testing boundary cases is non-negotiable. For example, ensure your solution works for matrices with only one element, matrices full of zeros, or matrices full of ones. This attention to detail will leave a positive impression on your interviewer. Now, let's look at some related problems that can help you deepen your understanding of matrix-based challenges. LeetCode 73, Set Matrix Zeros, involves marking rows and columns based on specific conditions, and it emphasizes the importance of not modifying the matrix prematurely. This is similar to avoiding side effects in the current problem. LeetCode 54, Spiral Matrix, tests your ability to navigate a matrix systematically, which is a useful skill for implementing efficient traversal patterns. LeetCode 361, Bomb Enemy, shares a key similarity in that it relies on pre-computing row and column information to optimize calculations. Finally, LeetCode 240, Search a 2D Matrix 2, demonstrates how to take advantage of sorted properties in a matrix to optimize searches. Studying these problems will not only help you solve this challenge but also build a strong foundation for tackling a variety of matrix-related questions in the future. To approach this problem, you have several strategies to consider. The brute force method involves checking each cell's row and column to see if it meets the condition. While this approach is straightforward to implement, its O(n)² time complexity can be inefficient for larger matrices, making it less practical under strict performance constraints. A more optimized alternative is to use row and column pre-computation. For example, you can pre-compute information like row sums or column counts and use these to validate each cell in constant time. Although this method still has an overall complexity of O(n)² due to the pre-computation step, it avoids redundant calculations during validation and is generally more efficient than pure brute force. If the matrix has sorted properties, you might also consider applying binary search within rows or columns. This approach can bring the complexity down to O(n*log(n) for an nxn matrix, but it's only applicable for matrices with specific structures, such as those with sorted rows or columns. Each of these methods has its trade-offs, so the best choice depends on the problem's constraints and the matrix's properties. Great job! In this session, we reviewed problem number 1582 and its solutions. You've learned key matrix traversal techniques and how to optimize for efficiency. Keep practicing and applying these strategies in your coding journey. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!